Today's topic is entropy. First, we define entropy. If some system absorbs heat at absolute temperature T by some reversible process, then change in its entropy ds is defined as ds equal to dq upon T. dq is the heat absorbed by the system at absolute temperature T. So, if at absolute temperature T, some system absorb dq heat, then change in its entropy ds is given by dq upon T. This is for reversible process. If heat is absorbed by the system, then its entropy increases. If heat is absorbed by the system, dq is positive, so ds is positive and its entropy increases. If a system rejects dq heat, then dq is negative, so ds will also be negative and entropy of the system decreases. Other definition of entropy is that it is a measure of disorder of system. If disorder of the system increases, entropy of the system increases. Unit of entropy is calorie per degree Kelvin. It is from this definition. dq is the heat and unit of heat is calorie. So, unit of entropy S will be calorie per degree Kelvin. Unit of temperature T is degree Kelvin. Now we see what is the physical significance of entropy. From this definition, ds equal to dq upon T, we have dq equal to Tds. This is also known as mathematical form of second law of thermodynamics. dq equal to Tds. So heat energy dq is given by ds into T. ds is change in entropy and T is absolute temperature. If we bring a particle of mass m at height h above Earth's surface, then its gravitational potential energy will increase by mgh. If we assume gravitational potential energy of mass m on Earth's surface equal to 0, gravitational potential energy at height h will be mgh, mass m, g gravitational acceleration and height h. If we compare these two equations 2 and 3, first is for dq, heat energy, and second is for gravitational potential energy, then we see that in equation 2 there is temperature, and temperature is measured, absolute temperature is measured from 0 degree Kelvin. Similarly, in relation 3 we have this height h corresponding to this temperature, because height h here is measured from a fixed level, that is level of Earth's surface. So in these two equations, temperature T, absolute temperature T is corresponding to height h. Then this change in entropy will correspond to mass m. So we see that first we see what is the physical significance of mass m. Mass m is a measure of inertia in translational motion, and similarly for rotational motion, measure of inertia is moment of inertia. In a similar way, we can now explain what is this change in entropy ds represent. In formula 2, absolute temperature T is measured from absolute zero temperature, and in formula 3, height h is measured from Earth's surface. If we consider temperature T corresponding to height h, then quantity corresponding to entropy will be mass m. So we can say that place of entropy S in thermal motion is same as that of mass m in translational motion, and that of moment of inertia in rotational motion. Since mass m and moment of inertia I are measures of inertia in translational motion and in rotational motion respectively, so we can say that entropy S is a measure of inertia in thermal motion. So we can call it as thermal inertia. This is the physical significance of entropy. Now we will prove that entropy is a point function. If a system goes from one state to another, change in entropy will depend on initial and final state only, and not on the path joining these two states. So entropy is not a path function and it is a point function. For this, we consider this figure showing a cyclic reversible process. In this figure, IAFBI, it is a reversible cycle. IAFBI. I is initial state and F is final state. A represent this one path, IAF. Similarly, B represent another path, FBI. So there are two paths joining these two states I and F, and this is a cyclic process. For this cyclic process, from Clausius theorem, we know that integral for this closed cyclic process, integral of dq upon t is 0, and this dq upon t is ds. So we have for the closed cyclic process, reversible process, integral ds for closed cycle is equal to 0. Now this closed cycle we can divide it into two parts. First is IAF and then FBI. So we can divide this integral for closed cycle into two parts. First one is from I to F, and here A is written for path A. I to F by path A. Then we go from F to I by path B. So second integral is F to I and B means from path B. So this integral ds for closed cycle can be written as integral I to F ds for path A plus integral F to I ds for path B, and the sum of these two integrals is equal to 0. Now the cycle is reversible. We can do the process in reverse direction also. So this second integral, we can write it as second integral, which is integral ds from F to I by path B. We can write it as minus integral I to F by path B ds. We change F to I by I to F, so we have an additional negative sign, and from this we can write as integral I to F ds for path A is equal to integral I to F ds by path B. So the change in entropy between two states depend on initial and final state only, and not on the path joining them. So we see that entropy is a point function and it is not a path function. Now we consider the topic to find an expression for change in entropy of an ideal gas change in entropy for ideal gas. We consider 1 mole ideal gas at pressure P, volume V and temperature T. If dq is the heat given to this, then from first law of thermodynamics we have dq equal to du plus dw. We consider 1 mole ideal gas, this is the system, and heat given to this system is dq, and from first law of thermodynamics we have dq equal to du plus dw. Here du is change in its internal energy, u is internal energy, so du is change in internal energy, and dw is work done by this system. Now we define Cv, molar specific heat at constant volume. Molar specific heat at constant volume, Cv, is defined as dq upon dt. Here T is capital T and it is absolute temperature, not small t, correct it. Definition of Cv is dq upon dt. dt is change in its temperature, and we write Cv, then this we represent that it is for at constant volume. So Cv is dq upon dt and it is for constant volume V. This definition of molar specific heat comes from the definition of specific heat, and definition of specific heat C comes from the relation dq equal to mc dt. If we consider a substance of mass m and we want to raise its temperature by dt, then heat required for it is dq equal to mc dt. C is constant, which is known as specific heat. If we consider molar specific heat, then we put this mass m as equal to 1 mole. So for 1 mole, this molar specific heat Cv becomes dq upon dt at constant V. Because it is at constant V and for constant volume V, work done dW, which is equal to pdV, now becomes 0. Because for constant volume V, dV is 0, so dW is 0. So we can write from first law of thermodynamics, that is equation 1. For constant volume, we can write dq equal to du. So Cv now becomes equal to du upon dt at constant V. We put dq equal to du. This gives expression for du, and du is equal to Cv dt. Also we have dW, work done by the system, equal to pdV. Now change in entropy, ds is defined as ds equal to dq upon t, and dq is du plus dw from equation 1, that is first law of thermodynamics. Now put the values of du and dw here. Value of du is Cv dt and value of dw is pdV. Put both the values here. We have ds equal to Cv dt plus pdV upon t. Change in entropy in going from initial state I, that is Pi, Vi, Ti, to final state F, that is Pf, Vf, Tf. For initial state, we write I. Here pressure is Pi, volume is Vi, and temperature is Ti. For final state, we write F. Here pressure is Pf, volume is Vf, and temperature is Tf. So if a system, that is 1 mole ideal gas, and this 1 mole ideal gas system goes from initial state I to final state F, change in its entropy delta S, that is SF minus Si, entropy in final state minus entropy in initial state, it is delta S, change in entropy, and it is equal to integral ds, integral from I to F. We put the value of ds from this relation. ds is Cv dt plus pdV upon t. So delta S, change in entropy, is given by integral I to F Cv dt plus pdV upon t. These are two integrals. First is integral Cv dt upon t, and second is integral pdV upon t. So we can write this integral as equal to integral I to F Cv dt upon t plus integral I to F pdV upon t. Now we have three variables P, V and T, pressure, volume and temperature. And if we consider only two from these three, then three combinations are possible. PV, second is VT, and third is TP. From P, V and T, if we take only two, we have three combination: PV, second VT, and third TP. So we find the expression for change in entropy of 1 mole ideal gas for these three combinations. First, we look at change in entropy in terms of temperature T and volume V. If we want to find the change in entropy in terms of T and V, we have to eliminate the third variable, that is P. And third variable P can be eliminated from this equation of state of 1 mole ideal gas, that is PV equal to RT. For n mole we have PV equal to nRT. Here we consider 1 mole ideal gas, then we have PV equal to RT. By using this equation we can eliminate P and find expression for change in entropy in terms of T and V. Here from this relation we have P equal to RT upon V. Substitute this value of P in this relation. We have delta S equal to integral I to F Cv dt upon T. First integral remains unchanged, and in second integral we put the value of P, that is RT upon V, so that second integral becomes R integral dV upon V. By putting P equal to RT upon V, T is cancelled out, R is constant, we bring it outside of integral, and we have this second integral as R integral I to F dV upon V, and first integral is Cv integral I to F dt upon T. Here also we take Cv out from this integral because it is constant. Now first integral is integral dt upon T, and value of this integral is log T. We write log T here as ln T. Ln T means log T. It is log at base E. So first integral gives Cv log T and limits are Ti to Tf. Similarly, second integral will become, R is constant, and second integral becomes log V, and limits are Vi to Vf. If we put these limits, we get Cv log, in first term we get Cv log Tf minus log Ti if we put the limits, and log Tf minus log Ti can be written as log Tf upon Ti. Similarly, in second integral, if we put the limits, then we have R log correct this expression also. It is not log Tf minus Ti. It is log Tf minus log Ti. And in this second term we have not log Vf minus Vi, but we have log Vf minus log Vi. If we put the limits, we get in first integral as log Tf minus log Ti, and in second integral we have log Vf minus log Vi. So correct these expressions, and then log Tf minus log Ti will becomes log Tf upon Ti, and similarly log Vf minus log Vi becomes log Vf upon Vi. So this is the change in entropy for 1 mole ideal gas in terms of T and V. Ln here represents log, that is log at base E. We can write R as Cp minus Cv. Now we take next combination. We want to find the change in entropy in terms of T and P. If we want to find the change in entropy in terms of T and P, we have to eliminate the third variable, that is V. And to eliminate V, we use this relation for 1 mole ideal gas, that is its equation of state, which is PV equal to RT. We have to eliminate V in this relation. We see here that V comes here as dV. We have to eliminate this dV. So to eliminate this dV, we use this relation PV equal to RT. If we differentiate it, we get P dV plus V dP equal to R dt. R is constant, and differentiation of PV gives P dV plus V dP. From this relation, we have P dV equal to R dt minus V dP. Here in this expression, we also again get the variable V. So this V can be eliminated from the relation PV equal to RT. So we put the value of V, that is RT upon P here. So P dV becomes R dt minus RT upon P dP. So we now eliminate V and put the value of P dV in this second integral. We put the value of P dV and get expression for change in entropy as delta S equal to integral I to F Cv dt upon T plus integral I to F R dt minus RT upon P dP. Now these are three integrals. In first one we get Cv constant and have Cv integral dt upon T. In second we have R constant and we get R integral dt upon T. If we put this value of P dV, that is R dt minus RT upon P dP, in this second term we get integral R dt upon T. It is not only R dt, it is R dt upon T. Correct this second integral. If we substitute the value of P dV, we get R dt upon T. So correct this second integral term, it is R dt upon T. R is taken constant and integral will become integral dt upon T. And in the third term, R is taken constant. T here is cancelled out and the remaining term here becomes R integral dP upon P with minus sign. In this integral, second integral, we have to divide by capital T because it is integral P dV upon capital T, and in this integral, this is the value of P dV. We have to divide it by T. so that the second integral becomes r integral dt upon t, and the third integral become minus r integral dp upon p. Now we can integrate this. Integral dt upon t is log t, and if we put the limits ti to tf, we get log tf minus log ti. Similarly, in second integral we have r log t and limits are ti to tf, which gives the second term as r log tf minus log ti. Third integral is minus r integral dp upon p, and this integral becomes log p, limits are pi to pf. So the third term becomes minus r log pf minus log pi. We can write this as cv log tf minus log ti becomes log tf upon ti. In first two terms, which is taken common, and remaining terms become cv plus r. So we have cv plus r into log tf minus tf upon ti. Log tf upon ti is for log tf minus log ti, and in last term we have minus r log pf upon pi. We can also write here the value of r, that is cp minus cv. And the third combination is to find the change in entropy in terms of pressure P and volume V. In terms of P and V, then we have to eliminate the third variable, that is T. And to eliminate this, we use this relation PV equal to RT. And from this relation, T is equal to PV upon R. We have to eliminate this T in this expression. Integral Cv dt upon t plus integral p dv upon t. So here we have to eliminate both t and dt. So t can be eliminated by using this relation t equal to pv upon r, and to eliminate dt we differentiate it. Differentiation of t gives dt equal to p dv plus v dp upon r. Substitute these two values of t and dt in this relation. We get the expression for change in entropy as delta S equal to integral I to f Cv, and this is the value of dt p dv plus v dp upon r, divided by t, and value of t is pv upon r. And in second integral we have plus integral I to f p dv upon t, and substitute here pv upon r for t. Now this first integral we can divide it into two parts. R is cancelled out here, and we have two integrals, as first is integral cv dv upon v, p also cancelled out, and in second integral we have cv dp upon p, v is cancelled out, and in third integral we have integral r dv upon v, p is cancelled out. So we have three integrals. Cv is constant taken outside the integration, and integral dv upon v gives log v, limits are vi to vf. In second integral we have cv constant taken outside the integral, and integral dp upon p gives log p, and limits are pi to pf. In third integral r is constant, and integral dv upon v is log v, limits are vi to vf. After putting the limits, we get Cv log Vf minus log Vi, that is log Vf upon Vi. In second term, we have Cv log Pf minus log Pi, that is log Pf upon Pi. And in third term we have R log Vf minus log Vi, that is R log Vf upon Vi. Log Vf upon Vi appears in two terms. We take it common and have Cv plus R into log Vf upon Vi, and the remaining term is Cv log Pf upon Pi. We can put here the value of R, that is Cp minus Cv. In this way, we can find the expression for change in entropy of 1 mole ideal gas in terms of PV, Vt and Tp for these three combinations. Now we can also find the change in entropy of ideal gas in isothermal process. For isothermal process, temperature remains constant, so Ti equal to Tf. So in the expression for delta S, change in entropy, if we have terms like log Tf upon Ti, that will become equal to log 1 and that will be equal to 0. So the terms having log Tf upon Ti becomes 0 for isothermal process, and we get expression for change in entropy delta S as minus Cp minus Cv log Pf upon Pi or minus R log Pf upon Pi. For isobaric process, we have pressure constant, that is Pi equal to Pf. So where we have the terms like log Pf upon Pi, it becomes log 1, that is equal to 0, and we can find the expression for change in entropy delta S as Cp log Vf upon Vi. For isochoric process, we have volume remains same, Vi equal to Vf. So where we have terms like log Vf upon Vi, it becomes log 1, that is 0. So change in entropy becomes delta S equal to Cv log Pf upon Pi. Remember this term, change in entropy of ideal gas in isothermal process. We have these two expressions. Delta S is equal to Cp minus Cv log Vf upon Vi, that is R log Vf upon Vi. If process is isothermal process and volume changes from Vi to Vf, change in entropy of 1 mole ideal gas is R log Vf upon Vi. Remember this formula. There is other expression also, that is delta S equal to minus R log Pf upon Pi. But in terms of volume, we have delta S, change in entropy, is R log Vf upon Vi. It is for 1 mole ideal gas. If we have n mole ideal gas, then we have delta S equal to, it is n times, it becomes n R log Vf upon Vi. So in isothermal process, if temperature remains constant and volume changes from Vi to Vf, change in entropy of 1 mole ideal gas is R log Vf upon Vi.